Consider the titration of 25 milliliters of 0.100 molarity HCHO2 with 0.100 molarity NaOH. Calculate the pH initially after 5 milliliters, 12.5 milliliters, 25 milliliters, 30 milliliters, and 50 milliliters. The Ka value is 1.8 times 10 to the negative fourth. First, to calculate the pH initially, since there is no NaOH yet to buffer it, we're just going to consider it as mixing HCHO2, our acid, with H2O, our water. This is going to go to H3O plus CHO2. Yeah. So we're going to do an ice table for this. And we're going to write in our molarity for the acid. This is not going to be considered as aqueous. And this is going to be 0. This is going to be 0. So this will be negative x, positive x, positive x. 0.100 minus x, positive x, positive x. Now we're going to plug it into the ice table equation with the K value. So 1.8 times 10 to the negative fourth equals x squared, because these two x's multiply by each other on the top, over 0.100 minus x on the bottom. Since our Ka value is small enough, we're going to take out the x on the bottom, and this will just be 1.8 times 10 to the negative fourth equals x squared over 0.100. Now we're going to do the calculations. So 1.8 times 10 to the negative fourth times 0.100 equals 0.00018, and then we're going to square root that because we're trying to get x. That means x will equal 0.00424. And then after this, we're going to take the negative log of this to find the pH. So the answer for the initial pH will be 2.37 equals the pH. We took the negative log of the the negative log of the x, because this can be considered as H3O plus at this point, and H3O plus, if you take the negative log of that, you're going to get pH. Okay, so now that we're actually adding a acid in it, it's going to become buffered a little bit, we're adding a base into it. So it's going to be buffered, and it's going to start making a conjugate base. So this equation is going to have to, this is like no longer going to be like this. It's going to be a neutralization equation. So first, let me write this out. So we're adding 5 milliliters of NaOH. So to write the neutralization equation, it's going to be HCHO2 plus our base, because this is a titration, you're adding the base to the acid, NaOH. The acid is going to donate to the base, and you're going to get H2O, and you're going to get the conjugate base of NaCHO2. So this is what you get. Now that we've got this, well, technically, I guess we can use this for later. So I should have calculated the molarity of NaOH first. That's what you really should do first. But I was just explaining how I'm getting good at, or how I'm going to get this, because we're going to use that in the rest of the equations for the most part. So to calculate the molarity, we're just going to do like normal. So 0.005, because we need liters. Got moles of NaOH equals 0.100. So 0.0005 is our moles of NaOH. Okay, so now we're going to put this over into here, but we also need to find how much moles we have of the acid. So we're just going to do the same thing. Equals the moles of HCHO2 over how much we're given. We're given 25 milliliters. That is the same as 0.025 liters. So this times 0.100 equals 0.025 moles of HCHO2. Okay, now that we've got that, we're going to put it over here finally. This is also not going to be, we're going to ignore this again because it's aqueous. And then this is going to be 0 for now because right now we don't have any conjugate base since this has not been calculated yet. But when we're going to titrate it, we're going to consider the least one with the moles. So what I mean by that is, look at these two. This one has the least amount. So we're going to subtract of this because it is going to be used up. And then it will be added over here because this is a product. This is going to disappear because all of the base is used up by the acid. And the acid will be left over as .002. And this is just 0.005. Oh, 0005. I should write that. Okay. Now what we're going to do is we're going to use the Hackl-Bock equation, which is pH equals the pKa plus the log of our base over acid. This conjugate base is our base, and our acid is this. So we're going to plug that in to find pKa. All it is the negative log of Ka. Our Ka is 1.8 times 10 to the negative fourth. So we're going to do 1.8 times 10 to the negative fourth log. And we're going to get that our pKa equals negative, oh, no, it equals positive because it's negative. So positive 3.74. So let's plug that into here. So 3.74 plus the log of our base over our acid. Then let's calculate that. It's negative, so 3.74 plus negative 0.602. And then you're going to get that our pH is 3.13. So then we're going to do 12.5 milliliters. So the thing about 12.5 milliliters is that it's half of our equivalence point. Our equivalence point would mean that the moles of the acid equals the moles of the base. So that means that it would be at 25 milliliters. Since both of these is 0.100 molarity, if you had 25 milliliters of each, that would equal the same moles. So this is going to be our equivalence point here. And with the, or this is our half equivalence. With the half equivalence point, the pKa equals the pH. So this can be solved. If you want to do all this work, you're going to end up figuring this out. But basically, what's going to happen is that you're going to subtract 12.5, or whatever you get of this, of the moles, you're going to subtract it here, and you're going to get like the same number of base and acid. And when you calculate something over the same of something, you're going to get 1, right? So that means that here, if you do this, you're going to get 1, and then you're going to try to log it, and it's going to be 0. So that's why that would cancel out, and it would just equal pKa. So our pKa was 3.74. So that is our pH. This is the most simple step of the whole thing. All you have to remember is that pKa equals pH. Okay. Our next step is the most complicated. So, got 25 milliliters added of NaOH. Okay. So, we're going to start out doing the same thing that we did in the other step when we added 5 milliliters. We're going to find the moles of NaOH. So 25 divided by 1,000, 0.025 moles NaOH equals our molarity. So we're going to get that we have 0.0025 moles of NaOH. Now, if you remember, that is the same amount of moles we have of our acid. You can see that, oh, this is the wrong page. Okay, anyways. Well, we do have the same amount of the acid, HCHO2. So our HCHO2 is the same moles of NaOH now. So we're going to set up our table like normal. So NaOH plus HCHO2 goes to H2O plus NaCHO2, and it's going to be 0.025 mole, 0.0025 mole, and this is ignored, and then this will be 0. So we're going to subtract 0.0025. It doesn't matter if it's the base or the acid, because in the end, these are both going to come out as 0. Because when you're at the equivalence point, both your base and your acid are both going to be used up. And the conjugate base is going to be at its max. So this is going to be 0.0025. That is going to be at its max. This is just what you end up with. So what you're going to do here is you're going to treat it as a base equilibrium problem. So this is the part you need to understand. We're going to switch this equation so that we can get the conjugate base as the reactant. So you're just going to switch it. So NaCHO2 plus H2O goes to NaOH plus HCHO2. And then we're just going to go ahead and plug this in. Oh wait, no, we're not, sorry. What we need to do, now that we're treating as a basic equilibrium ice problem, we need to find the molarity, because that is what you need for the ice problem. So we're going to take this number here, 0.0025, and we're going to divide it by our liters. So this is our moles, we're going to divide it by our liters, and we have 0.0025 liters plus 0.0025 liters. So 0.0025 divided by 0.005, you're going to get 0.5. Yeah, sorry, I messed that up. Sorry, it is actually 0.025 plus 0.025, not 0.025. This is our liters, not this. So you're not going to get 0.5. You're going to get okay, anyways, you're going to get 0.0500 molarity. Now we're going to plug that into here. So 0.05 molarity, and this nothing. This is going to be 0 and 0. Since it's used up here, we showed that it got used up, so there's no molarity. Well, there is a molarity, but the moles got used up, so it's going to come out as 0 for the molarity. So this is going to be negative x, positive x, positive x. 0.05 minus x, positive x, positive x. Now, our next step is we need to find the KB, because now we are working with a base. Because I said we're doing a base equilibrium problem. We're treating it as that. So, I don't know why I did that, but the KB times the KA equals KW. So let's plug in those values. Okay, now I know why I did that. I need to find the KA. KA was 1.8 times 10 to the negative fourth. So KB times 1.8 times 10 to the negative fourth equals KW, which is 1 times 10 to the negative 14th. Okay, so that means that we do the math. KB is going to come out as 5.55 times 10 to the negative 11th. Okay, so now we've got that. So we can finally do the ICE equation with the KB. So 5.55 times 10 to the negative 11th equals x squared, because those are the products, x times x, over 0.05 minus x. We're going to take this out again because this is another small value of KB, and we're going to do math. So okay, so x comes out as a very small number. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Making sure I'm writing that right. X is a very small number, but do not worry about this, because now that we are doing a base, we have a strong base. So this whole thing is a weak acid strong base equation, or titration. So since our base is so strong, we can use the rule that a strong base is going to fully dissociate, and so this can also be considered the same as OH negative, since it does fully dissociate. So all we're going to do now is we know that the POH equals the negative log of OH negative. So we're going to do this, and then we know that pH equals 14 minus POH. So let's take the negative log of this. We've got 5.778 as our negative log. 14 minus 5.778 comes out as 8.22. That is our pH for our equivalents, or yeah. Okay, next step, we're going to be doing 30 milliliters of added NaOH. Now, our base is the one in excess. So it's not going to change too much. It'll actually, in my opinion, it'll get easier from this point on, because the base is the strongest, and as I said up here, you can just consider whatever we get as X, just, you know, we can consider it as OH. So we're going to find our moles again. Okay, this times 0.100, you've got 0.003. Let's write in our equation. Goes to H2O plus NaCH02. Okay, this is going to be 0.003. This is the same as it has always been, which is 0.0025. This is not considered, like I said. This is 0. Okay, so we're not going to pay attention to this anymore since we're now working with the strong base. And now that this is the one in excess and this is the one that it's going to run out first, like before I said that the base was the one that ran out first, now it's the acid. So we're going to start subtracting the acid. So that would leave you with this is that, and we're ignoring this side like I said. Okay, you've got 0.0005. All we're going to do is find the molarity of that, and the molarity is going to equal OH negative, if that makes sense. So that's basically what we did here. We found X, which is molarity in the end, and then it equals this, I believe. But you know what? Ignore that. I'm just saying that the molarity of our base, since it is strong, is going to equal OH negative. So 0.005 over our liters, so 0.03 plus 0.025. It's going to equal 0.055. 0.0005 divided by 0.055. You're going to get 0.009. As I said, this equals the OH negative since it is a strong base, and we can just take the negative log of that. So you're going to get 2.04. That equals the POH 14 minus 2.04. 14 minus 2.04. You get 11.96 as your pH. Okay, it's the same exact thing for when we're working with 50 milliliters of added NaOH. Let's find the moles. So this step was just the same as this. I just did liters times the molarity. Okay, so we've got our moles. Let's set up our equation again. Okay, let's go ahead and plug it in. And since this is in the limiting one, we're going to subtract that. Equals that. Let's go ahead and find what the molarity of that is. So, .075. You're going to get 0.03333. Okay, we're going to take the negative log of that. Negative log of that is this. We're going to subtract that from our 14. And you're going to get 12.52, which is the pH of that.